Good morning dear students, my name is Radheshyam and in this video we'll discuss Vernier calipers. First we'll use a very specific case of Vernier calipers and then we'll generalize it. So let's say forget about all this. So let's say we have a main scale that can measure in centimeter and its long division in centimeter and subdivisions are in millimeter. So we'll say that main scale has least count of 1 millimeter, and we know that from this main scale we cannot measure any value smaller than this least count. So what do? We take 9 subdivision of main scale and using a secondary scale or Vernier scale. It is also called Vernier scale because this method was devised by Vernier and that's why this is called Vernier scale. So what we are doing essentially that we are taking 9 subdivision of main scale and that will become 9 millimeter, and we are dividing it into 10 parts of secondary subdivision, secondary scale subdivision. So from here you can see that this is 1 and this is less. So one mark on the secondary scale is a different point, and these number of subdivision are 10. There are 10 subdivision for each 9 subdivision of main scale. So from this we get this point: 9 subdivision of main scale is equal to 10 subdivision of Vernier scale, and from here we will get 1 subdivision of Vernier scale, and that will be 9 by 10 main scale reading, or you can say 9 by 10. So the 1 subdivision of Vernier scale will become 9 by 10 of main scale reading. So this suggests that 1 subdivision of Vernier scale can now measure 0.9 millimeter if we use it standalone, but we are not using it standalone, but we are using main scale and Vernier scale together. They are joined together, and when you will see construction, so this is essentially when there is no objects, both zeros are aligned, and when both zeros are aligned we say that there is no zero error. So this is the case of no zero error. No zero error, because when there is no object, the 0 of main scale and 0 of the Vernier scale all are aligned or matched on single line, and that's why there is no zero error. So from this we define a quantity that is called Vernier constant or least count of the measurement. So from this, using these two scales with different least count, because least count of this scale, main scale, is 1 millimeter and least count of Vernier scale is, secondary scale is 0.9 millimeter. Hopefully this is clear, because one subdivision of Vernier scale can now read 0.9 millimeter. So from here we get a quantity that is called Vernier constant, or the least count of the measurements from this Vernier scale, and that we defined 1 main scale subdivision reading. So 1 subdivision of main scale minus 1 subdivision of Vernier scale, and the difference of it will become 1 millimeter minus 0.9 millimeter, and from here we will get 0.1 millimeter or 0.1 centimeter. So from this two scale of different least counts, we have made a device that can measure 0.01 centimeter. So essentially it can measure 1/10 of main scale. So the least count of this vernier scale becomes 1/10 of main scale reading. Hopefully this is clear. And so from this, how do we read any value? What we do, we will put the object, and because of that, now let's say our main scale is like this. Main scale will be like this, and the vernier scale we slide it to measure the distance. So let's say that we have now got a situation like this, where the reading should be 1.1 centimeter and 1.2 centimeter. We know that main scale reading can at best measure 1.1 centimeter or 1.2 centimeter, but using this instrument, using this vernier calipers, we get to read now further than that. And how do we do that? Reading how dimension is read. So let's say that we have got this. So from this we know that the main scale reading is 1.1 centimeter, and from this we want to measure this distance, that what is the distance between 1.1 and the 0 of vernier calipers. We want to measure that distance. And so how that is measured? We say that, let's say that is the x number of subdivision of vernier calipers. X is the, so what do? We will write 1.1 centimeter plus least count of the vernier calipers into how many subdivision of vernier calipers from 0 to vernier calipers. So which subdivision of vernier calipers exactly matches with the subdivision of main scale, and we count that, and that count is x. So we x, what is x? So this value from 0 to number of subdivision on vernier scale that exactly matches with the main scale subdivision, and that we count how many of them are there. So we'll say that is number x, and we multiply it with the least count of the scale, and so we'll get a reading. Hopefully this makes sense. So in case, let's say we have got 5x. So let's say in this case we have find out that x, the subdivision on the vernier calipers is 5 subdivision that exactly matches with the main scale, and so the reading will become 1.1 centimeter plus 5 into least count of the vernier scale. So from this what we'll get? We'll get 1.15 centimeter. So whatever we are measuring, that dimension of that quantity is 1.15 centimeter. Hopefully this is clear. So if you have any doubt in this explanation, please ask. So what do we do with the general case? Idea remains same exactly. So what now we do, that we'll take n minus 1 subdivision of main scale, and we equate with the secondary scale n subdivision of secondary scale, and from here we will get one secondary scale or Vernier scale division, and that will be n minus 1 divided by n into main scale division. And from here we'll find out what is the Vernier constant or the least count of this device, and that is 1 main scale reading minus 1 Vernier scale reading or Vernier scale subdivision, and from here we'll get 1 by n main scale subdivision. So from this we get Vernier constant or the least count of this Vernier calipers, that is equal to 1 by n of main scale subdivision. And from here we will get reading will be, so let's say that we are getting n number of reading on main scale, and the fine tuning we get x number of subdivision on the Vernier scale that exactly matches with the main scale subdivision, and we count that number and we multiply that with least count of this device or Vernier constant, and we get a reading in the case of general case. Hopefully this is clear. We can also see that as this is the case of no zero, we'll build up on this concept in the. Okay, so let's continue our discussion in case of zero error. So when there is no object, and suppose that both jaws are aligned in such a way that 0 and zeros are aligned, then we say that there is no zero. So this is the case that we have just studied. So this is the case of there is no error, and this is the case when there is no object, but you can see that the Vernier scale is not aligned, but it is on the right side of 0 of main scale, and that's why this is called positive zero error. So even when there is no object, you can see that there is error and it will read some value. So this is called positive zero error. We'll calculate how to calculate this error, and after that, so after this, in this case you can see that 0 of main scale and the Vernier scale is left of the main scale. That's why this is called negative zero error. This is the case of negative zero error. When there is no object, there is an error, and because 0 of Vernier scale is on the left side of the 0 of main scale, it is called negative zero error. So now we need to have error correction. So whenever we'll measure object, whenever we'll measure length or dimension, this error will be always there. In case of any object, there will be this error, and in case of this also there will be this much error, this much positive error, and this much negative error will be always there. So what do? We have to make error correction. So error correction is always, the formula is that error is always corrected. Whatever error is there, will always subtract it from the reading. So whatever new reading will be there, we will subtract this error. So first of all, we need to calculate what will be the error. So let's say that we have calculated error to be, so we are saying that this is the positive zero error. So in case of error correction, so this is the first thing that we need to know, that error correction is always, what do? We always subtract error. Whatever will be the reading, will get. So suppose we are measuring from this instrument, and whatever reading will get, we from that reading will subtract this positive error, and in case of these two error correction we will subtract the negative error. The issue is that value will be different for both cases. So in case of this error correction we always subtract error correction. Whatever error is there will measure the reading as if there is no error, will measure reading, and from that reading will subtract this negative error, negative zero error. So the formula is same, but we calculate in a different way because this will be negative quantity, so this gets add up and this positive error is positive, so this is subtracted. So positive error, how do we calculate this positive error? So the formula becomes positive zero error. Let's say that it should be 2, so we'll write formula like this: n plus whatever will be the this. So let's say that the vernier scale is aligning at let's say that we know that how to read the, hopefully we know that how to read the vernier reading, so we'll read vernier reading, but in this case there is n, so this indicate value of n, where our zero starts, from which number it start, our zero starts, so it start from 2 onward, so we'll write n is equal to 2. So in this case will become, our value will become 2, and then we'll take vernier count into x. What is the this number x from 0 to where it is aligning with the main scale, so this becomes positive zero error. And in case of formula we write it like this n, and in our case we'll write this as 2 and then x into vernier count, and this value will be positive, and we'll subtract from the reading, whatever reading with this scale we get, whatever reading we'll get, we'll subtract this positive error because this quantity is positive. But in case of negative error, what we do, we'll get reading and negative error is calculated. So this is difficult part. So from, you can see from my example that it is starting from -3, so the -3 is the sub count, so we'll take -3, and if it is millimeter then we'll take millimeter, and then where this vernier number is or vernier count is aligning, so we'll take that x into vernier count, and this value will be negative, so whatever reading we'll get, we'll subtract this and we'll get addition. So you need to be very careful in case of negative zero error, because there is an advanced question on this concept only, and most of the books I have seen that it is given wrongly. So we have to be very careful in case of negative zero error. Positive zero error we hardly do mistake in case of positive zero error, so this is not an issue. But in case of negative zero error, you need to calculate like this, or you calculate from the right side, from this side, which value is, which number, which sub count is aligned, and that is the value, minus of that value is the error, negative error. So you can do from a right side if you want to take into consideration of only the aligned number, but if you can also measure it like this, because this is -3 subdivision, and we can do normal measurement, so there is no issue about that. So hopefully this makes sense. If you have any doubt, please ask question.